Hello, everybody. Welcome to today's lecture. Today we're going to cover chapter 3.2, where we're going to be dealing with probabilities involving where verbally we'd say the word and or. So, for example, what's the probability that we roll a 6 and we get tails if we were to roll a die and flip a coin at the same time, for example? What's the probability that both of them happen at the same time? Or for the word or, it could be what's the probability that we roll a 6 or get a tails. Okay. So we've already kind of seen this. We kind of did the same kind of idea in 3.1 with, let's see, when we were talking about drawing a red 4 right here. You could think of this another way, as if we rephrase this, it would be what's the probability of drawing a red card and a 4. So the word and means that both of those need to be true. It needs to be both red and 4. So that's going to be equivalent to just saying drawing a red 4. Okay, and we saw that ended up being 1 out of 26. So how do we get there? Because we can't always think of it that way. For example, with the rolling a 6 and getting tails, there's no way to rephrase that in order to do it how we were doing things before. Okay. So before we really get into it, we should first talk about what's called mutually exclusive events. Okay. Mutually exclusive events. These are events that have no outcomes in common. Okay. This is a little bit of a technical definition. There's an easier way to think about it. But let's think about this first. So events that have no outcomes in common. So just to remind you, events are a subset of the sample space. So if we have a sample space, like let's take one of our sample spaces back from all the way in the beginning of this chapter of 3.1 here. Like right here, for example, okay. If we just copy this, so this is the rolling a dice one, okay. So this is one of our sample spaces. Well, let's say our first event, we'll call it E1, is 1 and 2, okay. So this would be sorry, I guess that doesn't really make sense in this context. Let's just say 1. This would be the event that we roll a 1, okay. And let's say E2 is the event that we roll a 2, okay. Then these are two events and they don't have anything in common, right? This one is only rolling a 1, this one's only rolling a 2. There's no shared outcome here. So we would say these two events are mutually exclusive, okay? The words mutually exclusive, just in plain English, means that if one of them happens, the other one can't happen. And that's exactly what this means here. Okay, if they have no outcomes in common, then that means that they can't happen at the same time. Okay. So when events are mutually exclusive, it leads to a rule for the OR probabilities. But first of all, before we get to that rule, let's think about, okay, we don't know the rule for the and probabilities yet, but let's just try to reason with this. So E1 and E2 are mutually exclusive events. That means if one of them happens, the other one can't happen. So if we're looking for the probability that E1 happens and E2 happens, well, by definition, they can't both happen at the same time. So the probability that these both happen is going to be 0. Okay. And this is like the more mathematical definition of what mutually exclusive means. Okay. So if probability of A and B equals 0, then A and B are mutually exclusive. Okay, and vice versa. If we already know they're mutually exclusive, then we know that the probability of A and B is 0. So this will, now that we know this, okay, this is the true definition of mutually exclusive, then this can lead into what's called the OR rule. Okay. The OR rule is sometimes called the additive rule for probabilities, because that's what we end up doing is adding. So let A and B be any events. Then the probability that A or B happens, okay, so in this scenario, we just need one of them to happen, either one of them or both of them, okay? So the probability that at least one of them happens is going to be the probability that A happens plus the probability that B happens. But then we have to do one more thing here, which is, let me move this over. Okay, I'm going to move this over to the left here to make some room. We need to subtract off the probability that A and B happens. Okay, now why would we need to do that? Well, let's think about it like a Venn diagram. Okay. Let's say that this is the probability of A happening. Okay. This is the probability of B happening. Then right in the middle here would be A and B happening. Right, this is their overlap. This is where they both happen. Then if we're looking for the probability that one of them happens, then when we do the probability of A, we have this part, and then we add in the probability of B. But what just happened here is that, okay, when we do that, that means that we're counting this area of it twice because we counted it once in A and once in B. Okay, but we don't need this part to be counted twice. So to reconcile that, we subtract one of them off. So then we make sure it's only counted one time. So every part of this area is only counted one time. Okay. So that's why we subtract it off. Now, notice that if A and B are mutually exclusive, then we know the probability of A and B equals 0. So the probability of A or B can be simplified to the probability of A plus the probability of B. Okay, we don't need to subtract this off because we would just be doing minus 0. And if we were to look at a Venn diagram of these, whoops, what is that? So this is A. Oops. All right, that's A. That's B. It doesn't really matter which is which. I guess I had A as the blue one before. B is the red one. If two events are mutually exclusive, that means that they don't have any overlap at all. So if we were looking at a Venn diagram, there's no overlap. They're just completely separated like this. So we just do the probability of A plus the probability of B, and then we don't need to worry about counting part of it twice. So we don't have to worry about subtracting it off because there is no overlap. Okay. All right, so let's put this into action. Let's say what's the probability of rolling a 6 or getting tails. Okay. So we're doing two things separately here, right? So this is like event A, we can think of this as like event B. So we're rolling a die and flipping a coin simultaneously. What's the probability of at least one of these happening? Well, according to our formula, it's going to be the probability that the first one happens, which is rolling a 6, plus the probability of the second one happening, which is getting tails, minus the probability that they both happen. So the first thing we should ask ourselves is, are these mutually exclusive events? If we roll a 6, are we still able to get a tails? And the answer is yes, we are still able to do that, meaning they're not mutually exclusive, right? If one of them happens, the other one can still happen, okay? So something that would be mutually exclusive would be getting a tails and getting a heads, for example. You can only get one of those when you flip a coin. There's no way to get both of them. In this case, though, you can get both of them. So we could have a little bit of trouble here with that last probability because we haven't talked about the AND rule yet. So how do we know how to do that one? And the only real answer is, well, we could look at the sample space and look at all the different combinations. Okay. Later, like in a few minutes, we'll have a better rule for it. But for now, we'll just have to look at the sample space. So, these first two are relatively simple. Those are ones we did in the last chapter. Rolling a 6, that would be a 1 out of 6 chance. Getting a tails would be a 1 out of 2 chance. So the challenging one here is this AND probability. So let's go ahead and look at the sample space. Okay. So we're rolling a die and we're flipping a coin. So what are the possible combinations? Well, we could get a 1 and a heads, right? We could get a 2 and a heads, 3 and a heads, and then etc. for all the numbers. Or we could get a 1 and a tails, a 2 and a tails, etc. Okay, so these are all of the possible things that can happen. Looking at the sample space for the AND rule here. So there's 12 total possibilities, and this is the specific one of getting a 6 and a tails, the last one. So there's one way this can happen out of 12 total. So this is going to have a probability overall of 1/12. So just going from this line down here, we would have probability of rolling a 6 is 1/6 plus the probability of tails is 1/2 minus the probability of both of them is 1/12. Okay. And then you'll need your fraction rules for this one. So you should get 7/12. Or you can just use decimals. That's fine too. Which this would be about 0.583. All right. So that's the OR rule. This specifically right here is the OR rule. And if you have mutually exclusive events, this part goes away because it's just 0. And then you just have this first part. So now let's talk about the AND rule. Actually, well, before we do that, we need one definition. Just like mutually exclusive events are important for the OR rule, another kind of event called independent events are important for the AND rule. Okay. So two events are called independent if the occurrence of one event has no effect on the probability of the other event. Okay. So if one of them happening doesn't affect the other one happening. So if we just think back to rolling a die and flipping a coin, whatever you get for the die, it's not going to affect what you get on the coin, right? Those are two completely separate things, so we call those independent. If you were to flip a coin twice in a row, right, what you get on the first throw has nothing to do with what you get on the second throw, right? So we would call the first and second throw independent. So what are some examples of things that aren't independent, things that we would call dependent? Well, think about if we draw a card, right? So let's say we draw a card and it is the 4 of clubs, okay? So we draw that card and now it's out of the deck. We don't put it back in. So now what's the probability that we draw a 4 on the next one? Well, we already took one of the 4s out. So the probability that we draw a 4 is going to be 3 out of 51 cards that are left because there's 3 4 lefts and 51 cards left. If we hadn't drawn a 4, if we would have drawn, say, a 5, then the probability of drawing a 4 in the second draw would be 4 out of 51. Okay, there'd be 51 cards left, but there'd still be 4 4s. So what we get on the first draw does affect what we get on the second draw. Okay. So the two draws would not be independent. They would be what we call dependent. Now, in this section, in this chapter, we're just going to be assuming things are independent. Because as it turns out, the formula for if things aren't independent, we need what is called conditional probabilities, which we don't get into until 3.3. So we're not going to worry about that in this section. So in this section, we're just going to be looking at things that are independent. So let's look at this one right here. Well, actually, sorry, we need the rule first, don't we? Whoa, that's not what I meant to do. Hang on, I'll copy and paste that after I write down the rule. Okay. So for the AND rule, the probability that two events happen at the same time, if A and B are independent events, then the probability of A and B is equal to the probability of A times the probability of B. Okay. For this reason, it's sometimes called the multiplicative rule or the multiplication rule. Okay. So we just take the two probabilities and we multiply them together. Okay. If they're not independent, you need a different formula involving what's called a conditional probability. So here we're just going to assume they are. So let's think about this one. The probability of rolling a 6 and getting tails. We already know, from when we did the sample space here, that this should be 1/12, right? So using this rule, will we still get 1/12? Well, we know these are independent, so this should be the probability of rolling a 6 times the probability of getting tails. Rolling a 6 would be 1/6. Tails would be 1/2. So we do get 1/12. Okay. So we get the same thing using this rule instead of just using the sample space. Okay, what is the probability of getting 5 tails in a row? Well, like I said before, we can think of successive coin flips as independent events because whatever we get in the first throw, it's not going to affect what we get in the second throw. Okay. So here we only had 2 events, so we multiplied them together. But this extends to if we have 3 events, 4 events, 5 events, we just keep multiplying them together. So the probability of getting 5 tails in a row is going to be the probability of, I'll just say T for tails on the first throw times the probability of tails again, and then again, and then again, and then again. Okay. So we get 1/2 5 times, which sometimes you'd write as 1/2 to the 5th because there's 5 copies of 2, so you use the exponent there. But that number is not too big, so we can just do that, and it's 1/32. Okay. Okay. Let's think about. There's one more interesting rule here, which is related to the AND rule, which is called the at least once rule. Okay. If you go a little bit deeper into probability, you'd see this is related to something called the binomial distribution, which we end up using a lot. So this says if an experiment is repeated n times, the n trials are independent. Okay, so this would be something like the last problem we did where we get when we do tails, right? Um like getting tails 5 times in a row. So your experiment is flipping the coin. You do that 5 times. Here we're just using n as any number. All the 5 trials are independent. And the probability of A and P of A is the probability of A occurring one time. So this would be like 1/2 in the last example, right? The probability of getting tails one time. Then the probability that A occurs at least one time is 1 minus P of A complement to the n power. Okay. So it's a little bit strange. There's a few things you have to do here. First of all, so this is assuming you know the probability of A. First, you have to find the probability of A complement, which remember is 1 minus the probability of A. Then you have to take that and raise it to the n power, meaning you make the exponent however many times you're doing the trial. Then you're doing 1 minus that. Okay. So in this problem, we looked at the probability of getting 5 tails in a row. 1 out of 32. Not very good odds. What about the probability of getting at least 1 tails when, or better yet, what about the probability of getting at least 1 heads in 5 trials? Okay. We saw this is the probability of getting 5 tails every time. What's the probability that we get at least 1 heads in those 5 trials? Okay, so probability of getting at least 1 heads in 5 trials. Okay. Well, according to the formula, this is going to be the 1 minus the probability of getting a heads complement to the 5th power, because there's 5 trials. The probability of getting heads is 1/2. Okay. So the probability of getting heads is 1/2. So the probability of getting heads complement, which is the probability that you don't get heads, is 1 minus 1/2, which is also 1/2. Right. Which we don't really need the formula of that. The probability of not getting heads is the probability that we get tails, which would be 1/2. So up here, this one is 1 minus 1/2 to the 5th power, which is 1 minus 1 over 32, as we just saw, which would be 31 over 32. So this should make sense based on what we just did. The probability that we get tails every time in those 5 trials is 1 out of 32, right? The opposite of that, the complement, would be the probability that we get heads at least one time, which would be 1 minus 1 out of 32, which is 31 out of 32. So this adds up with what we did in the last section with complement probabilities. Okay. All right. So I think we're going to stop there for today. Um, so just make sure to practice these rules a little bit. The and the or rules, they do come up a lot. Um, and sometimes they can be avoided, like how we did the and one right here, using the sample space instead. So really, these are just ways to make the problem a little bit easier. Like usually, if you default to the sample space, you'll get the answer that way. It's just that the sample space could be very large, so we don't always want to have to do that. Okay. So just make sure you practice the formulas, and yeah, that's gonna be it for today. So I'll see you guys next time. So thank you for watching.